So you may have a lot of questions about the Big Bang Theory still, but in general, things that haven't been cleared up yet in what I've explained so far in Chapter 17 is how do we have this overall structure of our universe that we know to date. So like in Chapter 16, I talked about the fact that the universe is kind of these void areas and kind of galaxies arranged in clusters and superclusters on kind of walls. Where did that structure come from? And why in general does it seem, when all things are considered, that the distribution of matter is so uniform throughout our universe? And why does it look like the density of the universe is very close to the critical density? And so if we introduce something called inflation, which I know I mentioned inflation earlier, it would have happened near the end of the, or at the end of the gut era. If we introduce inflation, these things kind of fall into place. So what is inflation? Inflation actually is a really rapid expansion of the fabric of space-time of our universe very early on in our universe's history. And I've heard it put recently that this expansion, inflation, actually the fabric of space and time was moving faster or accelerating, moving faster than the speed of light, which, you know, that just blows my mind. But a lot of things in this subject blow my mind. So during inflation, actually, with our universe got these kind of little tiny perturbations or little tiny ripples, and these ripples actually, in the next few slides, we're going to call these ripples kind of seeds within our universe, where, in my estimation, these kind of seeds could be protogalactic clouds where galaxies could form, stars full of galaxies could ultimately form. So that's what inflation is, and that's kind of how it helps explain our overall structure. So it's just a crazy sort of expansion early on very early on in the history of our universe. So one of the things that inflation helps to explain is that as we look at this kind of background hiss of the early part of the history of our universe, we can see these locations, location A and location B, that look identical. And so it seems like they were quite possibly near each other at the time of the Big Bang. So here's how inflation helps that. So, for instance, looking back in time, location A, the space-time of A and the space-time of B actually were next to each other for the first, fraction of a second. And then we have inflation, okay, and these particles moved out here, and then after the 10 to the negative 36 seconds after the Big Bang, then's when we have regular expansion accelerated expansion of our universe. So I'm going to play this little animation for you. It's just basically this same figure animated. It's pretty cool though. So here we have at the time of the Big Bang, all matter and energy was in a very, very small place we call singularity. So here we go. Inflation, normal expansion. I like that. Did you see where it kind of showed it hit that sweet mark of going from the era of nuclei to the era of atoms? So, hope that helps. Okay, so inflation helps. So here are three kind of scenarios showing you kind of the fabric of space-time as it relates to the amount of density, the overall density of our universe. Okay, and inflation helps kind of show a sort of flat universe as we see it. So, for instance, if we are kind of an ant on picture, we are the ant, right? And so with inflation, we do end up with a kind of a, relatively speaking to us, kind of a flat fabric of space-time. It's the way I look at it anyway. Well, with all sorts of fancy calculations, actually we can, after applying introducing theory into the Big Bang theory, or introducing inflation in the Big Bang theory, we can actually use the information from the what we call the cosmic microwave background information to come up with some reinforcement of some basic tenets of what we observe. But before I go on to that, let me kind of show you that those seeds I mentioned on the cosmic background radiation that can ultimately maybe become these protogalactic clouds, actually they have a particular angular separation in general that they are from one another. So from this cosmic microwave background, which is what CMB stands for, we can estimate that our geometry is flat because the total mass plus the energy is at the general, what we call critical density. The amount of matter in the universe is about 28% of the total matter-energy combination. Only 4.6% of our universe is ordinary matter, and 23% of our universe is dark matter. And that leaves the balance of 72%, which is an awful lot, is what we call dark energy. Again, looking at the cosmic microwave background radiation, we can estimate the age of our universe to be 13.7 billion years old. Now there at the bottom, remember we talked about those weakly interacting massive particles back in chapter 16, that things are falling into place pretty darn well when we add inflation to the Big Bang theory.